Now is we spoke about this three-term Taylor method, and that used implicit differentiation. We needed a second derivative, and you can push that further. And I mean, theoretically, we can talk about a four-term Taylor, five-term Taylor, six-term Taylor. But the issue is you're needing all this implicit differentiation to find higher and higher derivatives, and mathematically, it's kind of a pain in the it's a pain. And so maybe is there a better way is what we're looking at. So we wrote it down the bottom. Three-term Taylor is certainly an improvement. The local error is smaller. Global error is smaller. The problem is, yeah. So we're going to look at something called Heinz method. So alternative is to improve Euler's method. So we got to start seeing the problem with Euler's method. So the following is a damped harmonic oscillator. Sorry, just damped oscillator with m going like this, lambda like this, u, etc. So this probably should have been in our lab. So this is dv dt is equal to minus lambda over m v of t. And of course, dividing by 0.1, dividing by a small number is actually multiplying by a big number. So you get minus 15 times v of t. Okay, so in this problem, which you should see, the extreme value of the derivative near t equal to 0 leads to a negative approximation to v at 0.1. So at this point, which we might call, we can call it whatever we want. How about, so v dashed of 0 is equal to minus 15 times v, which is minus 15 times a fifth, which is minus 3. Now, I'm not saying that's extreme or anything, but look, it is what it is. Now, the issue is that the slope is actually changing. The slope is actually getting smaller, but Euler's method assumes that the slope is the same over the full interval. So this is kind of taking m to be minus 3, whereas it might be the case that the slope, now you could say decreases in absolute value, but it's actually increasing because it's going from minus 3. And as time goes on, it gets up to 0. So that's increasing. So you get a problem here. And it should be obvious. So like if you actually do this, you're going to have a negative velocity after 0.1 of a second, which is just nonsense. The problem is, remember what is Euler's method? What is one of the issues with Euler's method? Is the second derivative. So we've got the error in Euler's method. Let's write it like this, is order of the second derivative. I'm just going to write second derivative like that. And if we look at the second derivative of dv dt, we'll actually have to use implicit differentiation, but we'll do it here. So the second derivative of v is minus 15. Now then you have to differentiate v of t, and the derivative of v of t is dv dt, which is also minus 15 v of t. Look, the derivative of v is minus 15v. So if I'm differentiating this a second time, I fix the minus 15, and then the derivative of v is minus 15v. So this is equal to 225 times v. And v is equal to 0.2. So that's equal to 45. The second derivative is 45. That is a very large. So actually it says the extreme value of the derivative. That really there should say second derivative. What that means is that the slope is changing very, very quickly near t equals 0. And therefore we're going to have big errors with Euler. Like this is predicting that at this point, the second derivative being 45, the slope is going to go from minus 3 to plus 42 if it doesn't change. So big second derivative, big problems for Euler. Okay, one method to improve the estimate is to try and use a line that averages the slope at x0 and x1. So maybe average the slope at x0 and that should be t equals 0 and t equal to 0.1. So how about we average the slope between those 2 points? Okay, so this is called Heinz method. So what what you do is you do Euler's method first. And this will be called, so this in this notation would be called, say, T1 and then V1 predictor. So this little 0 is called a predictor. Now you can iterate this and get better and better iterations, but we won't be doing that. So we're just going to, so this 0 means, I could nearly start putting a P on that. I won't, but that's what you can imagine it as. It's a predictor of what's happening at the next one. It's not a good prediction, but it's a prediction nonetheless. And what we can do is average out, essentially average out 2 predictions to get a better prediction. Okay, so we do Euler's method and we predict what the value of y will be at the next point. You see, the slope at the next point is often going to depend on y at the next point. So I'm saying the slope at, say, x1, y1, look, it's right there. So this is slope at x1 at the next point depends on the y value. So if I want to average the slope at, say, t equals 0 and t equals 0.1, I have to have an idea of what's happening at t equals 0.1. I need some kind of an idea of the y value. So that's where Euler's, the Euler predictor comes in. So then we take the average of these 2 slopes. So we're going to take, let's write this down. So some kind of m average would be the slope at the initial point. Now, if you just use that, that's Euler's method. So what Heinz method says is use Euler to predict what's happening at x1. And we call that y10. And then take the slope at the previous point and the predicted next point and average them out. So this is the average of, I'll say, initial slope and the predicted Euler predicted next slope. Let's write E there for Euler. Euler predicted next slope. Now I'm just going to write y dashed for slope k plus 1 for next, just because I'm running out of space. And use the initial point and this slope, this average of 2 slopes, to estimate y of x1. That's Heinz method. Right now, the equation of the line, we find that the next y value is the previous y value plus the step size times this slope, which would be f of, now I should probably be doing this with x1, shouldn't I? I don't know, we'll just keep on going. So xk, yk plus f of at the next point. And how do we know what's going on with y at the next point? We use that 0 means an Euler predictor. So we're averaging out 2 slopes. So that's just a thing. So it's called predictor corrector. So this is the predictor. And then I don't know if we have the corrector, to be honest with you, but you can think of it like this. So there's 2 approximations. So essentially what we're going to do is there's kind of, there's 3 points that are used. So in the first place, now I know I'm writing on top of writing, but you use this point here to predict what's going on here. That's your Euler predictor. And then you combine what's going on this initial point and the next point according to Euler, and you average out the slope according to the differential equation at both those points. And that's Heinz method. Okay. So we'll see, we got a picture here. So we'll do kind of what I did there. So we've got an initial point that we know about. We'll call this initial. Now Euler says, look at the, now the blue curve must be the exact one. Euler says, look at the initial point. I'm just going to call it initial point. Look at the slope of the tangent to the blue curve. That's the red yoke. And that's your Euler predictor. Well, that's, well, Euler's method essentially. So I'll say Euler's method. And in this context, it's a predictor. And it predicts that at x1, you're going to be here. So this is the Euler predicted, I'm just going to write next, as in the next point. That's where you expect it to be. So you got the initial point and where Euler thinks your next one is. Now, the Euler predicted next is a perfectly good approximation. It can be made better by making the step size smaller. Now what we want to do is, rather than make the step size smaller, we want to be a smarter method. What we want to do is we want to take two slopes, the slope here and the slope here. Now the slope here is just the Euler method. So the slope of this is m1. But what this other m2 is, so the differential equation, so you give the, this is a point here. Let's give it some thing. So we call this x1, y1, 0. And you can put that into the differential equation. So into the dy dx is equal to big F of xy. And you'll get, if this was a point, this Euler predicted next point, if this point was a point on the curve, that's not, but if it was, what does the differential equation say the slope would be there? And it would say what would be the tangent, and that's this blue line up the top. So the slope of this line is m2. So you got the m1 and the m2. Now if you can imagine, now I'm not sure how you do this exactly. It's not exactly how, it's certainly not how I'm about to do it, but not a million miles off. So this is not exactly right, because you have to think slopes are actually tangents. So like you have to do a bit of work to work. So you're working with like the tan of A plus the tan of B all over 2. And it's not the same as tan of A plus B over 2. I'm fairly sure they're not the same thing, but I'm going to draw the picture as if they are. So I'm going to draw a line in between the blue line with M2 and the red line with M1, and just kind of go halfway through and take that slope. So that's what this green line down here is kind of representing. That's the Heun prediction. And it's averaging out the two slopes. So look at M1, that says there's a big slope. Look at M2, that says there's a small slope at the next point. So rather than going just along the big slope, the big M1, take account of what might happen at the next point, and so do an average of M1 and M2. And so you end up with this Euler prediction here, or excuse me, Heun, which we call x1, y1. And look, it's got a much smaller error. Okay, because it takes into account, look at the blue exact curve, the slope is decreasing. And the Euler predictor allows us to take account of this. Okay, let's see. So this is a theory example. Consider an initial value problem. Heinz method uses two slopes, one calculated from the initial point and one calculated from the Euler predicted next point. So this is kind of initial and Euler predicted next point. And the approximation is because this is approximated by this. So how is y10 found? It's basically Euler's method. So y10 is equal to the previous y value plus the step size times the previous slope, which I'm fairly confident you can just write y dash of 0 here. Small comment. So I think you can see now where the iteration can come from. So we use 2 points, the initial point and the Euler predicted next point. Now what you could do is you could go back and use a different color altogether. You could go again, use this point and this point and play Heinz method again and keep doing it until you get some kind of convergence. You could do that. We're not going to bother, but you could. Right, how is y1 found? So y1 is we're going to average these two. Now, yeah, so I think we're probably just going to write down the formula, are we? So we're going to say the next y value is the previous y value, plus the step size, and now we're going to average two slopes. The slope at the initial point, x0, y0, plus the slope at the predicted point where the y coordinate is as predicted by Euler's method. So this yoke here is an average slope. Now I appreciate I'm repeating myself. Some of you will understand what's going on. Some of us, these extra explanations hopefully help. How is y 0 to? So this one is you from the Heun place. So from x1, y1, where you just found y1. y20 is an Euler predicted thing. So it'll be the previous y value, which is y1. Now it's very, very important. Very, very important. It's not y10. So we'll probably go up to the picture in the top after I finish writing here and explain why that's really important. That's going to be the mistake that most of you are going to make. Plus step size times previous slope. Now I can't really just write y dashed of 0 here. So I need to say the slope at the previous point. And again, this should be y1, not the predictor. Okay, so why am I making this big deal? Go back up the top here. So you've done one iteration and you're at x1 and you want to go to the next point. The Euler Predictor, which is this red thing here, this only helped us find this. This is now where we are. Now here, why would we use the Euler Predictor? We've got a better idea of the values. So you wouldn't use the Euler Predictor to jump off. You wouldn't jump off the Euler Predictor. Forget about that now. You've used it. Now forget about it. Now you're here. This is the Heun approximation. You're going to jump off here. That's why this is y1, not y1 predictor. And as far as you're concerned, the error here, so in this picture it kind of coincides. Look, the difference between that green, that x1, y1 and the green and the exact solution is a lot smaller than the difference between the Euler predictor and the exact solution. So if you're trying to estimate the slope, again, you would use y1 and not y10. Okay. Now we're looking at this formula. What's the question? What does f of x, I, y, I represent? The slope at the, you can say the previous kind of, or the current, slope at current point. Current point. What does this? So this is the next point, but the y as predicted by Euler. So this is the slope at next point as predicted by Euler. Why is the second term divided by 2? Because we're averaging two slopes. Okay, so that's a little theory question. Here's another one. Okay, now we're actually going to do Heinz method. So consider the initial value problem. dy dx is y minus 2x. Now this is not y by x. This is just y. Y of x is just y. Use Heinz method with step size 0.5 to estimate what's going on at 2.5. So just to give some global understanding, we're currently at x equal to 1. And we're trying to figure out what's going on at 2.5, and we're going in steps of 0.5. So we're going to go to 1.5, we're going to go to 2, and then we're going to go to 2.5. We're going to use Heinz method. Okay. So first thing you do is you predict, starting at x equal to 1, y equal to 0, what's going to happen at the next point. So what we're saying here is I want to average the slopes at x equal to 1 and x equal to 1.5 to get a good approximation of what's happening at 1.5. I have the slope, for once I have the correct slope at the initial point. And what I can do is I can estimate what's going on at x equal to 1.5, where will we be, and use that point to estimate the slope at the next point and then average the slopes at x equal to 1 and x equal to 1.5. So the first thing we have to do is estimate the y value at 1.5. So now this isn't our very good approximation of 1.5, but nonetheless it is an approximation to what's going on at 1.5. This is what we call y1 predictor. It's the previous one. Now at this stage you should know what Euler's method says. So Euler's method says the next y value is the previous y value is 0. plus the step size, which is 0.5, times the slope at the previous point. Now the slope is from the differential equation, y minus 2x. The previous y is 0, minus 2 times the previous x is 1. So if we do this properly, I think this gives us minus 1. So we get a prediction, not a good one, but an Euler prediction for what's happening at 1.5. I'm just going to put in the y value, is that the y value is equal to minus 1. Okay, so now what we're going to do is we're going to use those 2 bits points, the y equal to 0 essentially and the y equal to minus 1. Now it's a point, so it's an x and a y really. And look, x and y comes into the derivative. So really what I want to say, maybe I should just be more careful here, even if there's no space. So x equal to 1.5, y equal to minus 1. So use these 2 slopes according to the differential equation and average them out. So a better guess of what's going on at 1.5 is approximated by y1. Now I won't write Heun on it, but you could. It's equal to the previous y value, which is 0, plus the step size, which is 0.5. And now average the 2 slopes. Okay. Now the slope is y minus 2x. So the first one, the previous y value, I'm looking at these 2 points on the left, y minus 2x, plus, now do y minus 2x for the next point, y minus 2x. Now I'm just going to cheat by looking down here. I know that this is going to give us minus 1.5. If I go into the calculator. So I've got an approximation, which is now for what's actually going on at 1.5. I combine these 2 and I get x equal to 1.5. My best guess is minus 1.5. Okay, so now what I'm going to do is I'm going to jump from here to what's going on at 2, and I'm going to combine what's going on at 2 with what's going on at 1.5 to come up with a better approximation. So I do a rough guess at what's going on at x equal to 2 to get a good guess for what's going on at x equal to 2. So let's see how we get on here. So the y value at 2, which I don't really like, I really shouldn't even put, because we're not going to use this as an approximation to really. Y2 predictor is the previous y value. So we do not go to this. We've used that. This is our best estimate of what y is at the previous point. Plus step size, which is 0.5, and then times previous slope. Now the slope is 2, was it? Y minus 2x. So I should do y minus 1.5 minus twice x 1.5. I'm just going to go to the next page to see how I am for space. Yeah, grand. Loads of space here, so we'll actually go into the calculator with this. Minus 1.5 plus 0.5 times minus 1.5 minus 3. So I get minus 3.75. Now that's only a shout for what's going on at x equal to 2. Now I'm going to combine the orange point there in the top left hand corner and this point. So the other point that's with the orange is at x equal to 2, we've got minus 3.75. So we're going to combine two points, x equal to 1.5 and our Heun approximation with an x equal to 2 and our Euler predictor. I think both of them hopefully are on the next page. Yeah. So then we're going to do Heinz method now. So y of 2 is approximately y of 2 equal to previous y value. What's our previous y value? Minus 1.5. Plus step size is 0.5, and then average out the 2 slopes. So the slope at the first point, y minus 2x, y minus 2x, plus the Euler predicted next point, y minus 2x. Now I'm not going to bang that into the calculator, so that's the slope at where I am, and at the Euler predicted next point, this is equal to, as far as I know, it's equal minus 4.5625. Now I'm going to jump from here, this point, x equal to 2 minus 4.5625, that's where I am, to estimate, well, just get an Euler predictor for what's happening at the next point, so that'll be y30, is the previous y value, which is minus 4.5625, plus the step size, which is 0.5, times the previous slope, y, minus 4.5625, minus twice x. And I'm going to go into the calculator just to make sure that there's no rounding here or whatever. So minus 4.5625 plus 0.5 times minus 4.5625 minus 4. Yeah, I'm getting rounding here. So this is only approximately, so I'm introducing rounding, not a great idea, minus 8.844, because I understand Heinz Method has errors, and I'm adding to the errors now with my lazy rounding. I could do it at 6 significant figures, or maybe I will. Let me just fix this. So this is actually 84375. And now we do Heinz Method. So we have, this is where Heinz says we are at x equal to 2, and this is where, so we're going to not add these rounding errors. And this is where Euler thinks we're going to be, well, with this y value. So our final approximation to what's happening at 2.5 is to take the previous y value minus 4.5625 plus the step size is 0.5, and then average two slopes. The first slope, which is according to Heun, y minus 2x minus 4.5, now I remember why I round these things, 45625 minus twice x, plus the slope at the Euler predicted next point. So the y value is minus 8.84375 minus twice x, well here the x is 2.5. And this is, well, we'll see what the calculator comes up with, minus 4.5625 plus 0.5, that will be to be divided by 2, minus 4.5625 minus 4, minus 8.84375 minus 5, and there's loads of significant figures. This is probably the time to round at the end rather than earlier. And let's go at 5 significant figures, minus 10.164. Okay, so the rounding error is due to something else. So actually this should be an equals. Okay, in a table it looks something like this. Okay, so these y values are approximations. Although we have a large step size, using Heinz method means the approximations are relatively okay. Could use h equal to 0.1 to reduce the global error by a factor of 25. This is because the global error with Heun is order h squared. So if you reduce h by 0.5 to 0.1, that's dividing by 5. Because the global error is order h squared, it'll be divided by 5 squared, essentially, divided by 25. Okay. Yeah. This obviously is okay. So the exact value, so we're going to look at the error here. So I'm probably going to pause and write that down.